Hi everyone and welcome back to my flight mechanics class. So today's lecture is going to be based on modern flight dynamics by David Schmidt, and we're going to be covering the generic rotational EOM. So essentially this is going to be the same thing as the generic translational EOM, but applied to rotational dynamics. So we're going to start with an element of volume dV located arbitrarily on the aircraft, and we're going to be deriving the time rate of change of angular momentum for that elemental volume dV. So the first step is to actually start with a time rate of change of linear momentum for that elemental volume dV. So on the right hand side you have your sum of the forces, and that is the weight vector and the exterior forces, and then on the left hand side you have your dm times the inertial acceleration. So to shift to the time rate of change of the angular momentum for that elemental volume dV, you have to cross each of those terms in the equation with the position vector p prime. Finally, to expand that to the entire aircraft and derive the time rate of change of the total angular momentum, you have to use integration, and that is a volume integral to cross p prime with the weight vector, and a surface integral to cross p prime with the exterior forces. And that is because the weight vector is applied to the volume of the aircraft, and the exterior forces are applied to the surface of the aircraft. So this is very good, but ultimately not very useful. And the reason for that is because everything is expressed in terms of p prime only. And actually, what we really want is to express all of that in terms of pv, the position vector of the center of mass of the aircraft, and p, the position vector of the elemental volume dv. So you have a left-hand side and a right-hand side to the equation, and what we want to do is to take each side separately and to expand and rearrange them on their own, and once you're done with that, to equate them back with each other and see what it yields. So the left-hand side can be expanded using the derivative, and you will see that the first integral on the right will actually be equal to 0 because dp prime over dt is actually crossed with itself. And then the surviving term on the right, you're going to see that we can actually rearrange the position vector p prime in terms of pv and p, and that will yield the integrals at the bottom. So pv can actually be taken out of the integral because it is not dependent on dv. So this is the first step for the left-hand side. So now we're going to do exactly the same thing for the right-hand side. We're going to express p prime in terms of pv and p, and this is going to yield the integrals at the bottom, and they are separated in terms of those that contain pv, and that is on the left, and those that contain p on the right. So now that we've done that, we can actually equate the left-hand side and the right-hand side back with each other, and you will notice that the terms underlined in red, and that is this one for the left-hand side and that one for the right-hand side, are actually gone. And the reason for that is because they're equal to each other. And when you equate the left-hand side with the right-hand side, they cancel each other out. So an additional simplification that you can make on the right is that volume integral of p cross rho v times g times dv. So that can actually be rearranged as the volume integral of p times rho v times dv cross g. And the term on the left, and that is the volume integral of p times g times rho v times dv, is actually the first moment of mass, and we've figured out in the last lecture that this was actually equal to 0. So that whole term is actually equal to 0, and you're left with what you have at the bottom. So an additional simplification that you can make is to express the derivative term, that is dp prime over dt, in terms of pv and p, and what you will get is what you have on the right. And the first volume integral is actually equal to 0 because of the first moment of mass again. So dpv over dt only yields a translational term, and that will be cancelled out by the first moment of mass, and that is the volume integral of rho v times p times dv. And for the dp over dt term, that will actually yield a translational and a rotational term, and the rotational term will survive. And for that reason, the volume integral on the right will actually survive and is not equal to 0. So finally, you're left with what you have at the top. And the final rearranging that you can do is to express the inertial velocity of point P as the velocity of P within the body frame, and that is dP over dt, plus the contribution of the rotation of the body frame with respect to the inertial frame to the inertial velocity of P, and that is captured by omega vi cross P times dV. So that will be your final result, and that will be it for today. Thank you very much for listening. See you next time.